In this video, I'm going to show you how to solve a fairly complicated projectile motion problem. I call this a cliff problem because this is Red Elk. He throws a ball with a purely horizontal velocity, and that's what makes it a cliff problem for me. From the roof of a building that's 21 meters tall, it strikes the ground 17 meters from the base of the building here. Okay, so what's going on here is we've got a building. The ball is projected out this way. This is 21 meters here. And the ball kind of goes and hits here at about 17 meters from the base of the building, right? It follows this trajectory, which is roughly a parabola upside down like that. Okay? Now, when you solve these problems, there's certain things that are always true. Like, for example, our vertical acceleration, because we're on Earth, is always negative 9.81. Okay? The horizontal acceleration, unless the projectile has like jet engines or something on it, right? The horizontal acceleration is always 0, which makes these guys the same, right? When these guys are the same, the only formula you're ever going to use in the horizontal direction is S equals U times T. Now I know the formula is plus 1/2 AT squared, but the A is 0, so it's just S equals UT, okay? So this object's going to move with a constant horizontal velocity the whole time it's in the air, but the vertical velocity will change. Now, in a cliff problem, because it's a purely horizontal velocity, I think also our initial velocity is 0, okay? And that's because it's purely horizontal. And I just set these up. These are two linear kinematics equations. This is displacement, initial velocity, final acceleration, and time. And they're totally independent of each other with the exception of time. Time is the same thing on both sides. In other words, it's going to stop moving up and down at the same time it moves side to side. Okay, now I just need I need a couple more things here. I think the horizontal displacement is our 17 meters, right? So that's 17 meters. And then our vertical displacement is that we go down 21 meters. And now I think we can solve for everything on this side, and then we can solve for everything on this side once we get the time. Okay? So let's just solve away here. The final velocity, I'm going to use v squared is u squared plus 2as. Okay, and so the absolute value of the final velocity is square root of 2 times negative 9.81 times negative 21, right? So let's go the square root of 2 times negative 21 times, when nobody's looking, I just type those in as positive, and 20.298. So the absolute value of V is 20.298. Now we scratch our head a little bit. Obviously the object's going to be moving down when it strikes the ground, so we use, instead of the positive answer, we use the negative answer. But we can do that because it's in the square root of a square, right? So 20.298. And I'm carrying along some extra digits because why not? Okay? I don't want to round because that'll make me off later. And then for time, I can use S equals U T plus 1/2 A T squared. Okay, so let's see, T is going to equal the square root of 2 times negative 21 over negative 9.81. Okay. So the square root of 2 times 21 divided by 9.81. I didn't put the negative in there because, well, you know it goes away, don't you? Okay, so this is 2.0691. Okay, I'm just going to store that in a variable because I want to use the exact value. Now, once you get the time is on both sides. So once you get the time, you can kind of castle that across 2.0691. Okay, and now since S equals UT, U is going to be equal to S divided by T, right? So it's 17 meters divided by 2.0691. I'm actually going to use the value here, right? 17 divided by whatever I put in T, right? And I get 8.216 meters per second. Okay. And then, of course, the final velocity is the same thing, 8.216 meters per second. These guys are meters per second, okay? So now let's see what questions we need to answer here. The first one says, what time is the ball in the air? Well, about 2.1 seconds, right? Because we got 2.069, so with 2 sig figs we'd say that. And then B says, what's the velocity of impact in terms of an angle and a magnitude? Well, we got to take this guy here, right? And we got to make that into an angle magnitude vector, right? Okay, so let's just draw a picture of that guy. Right here, right before it hits the ground, it's moving over and down. Its vector looks like this. Over, down. Okay. It is 8.216 over and 20.298 down. Okay. I'm going to find that angle. I'm going to find that magnitude. That magnitude is going to be the square root of 8.216 squared plus 20.298 squared. All right. Let's do this. I'm going to store that guy as my V just for fun. Okay. So now I'm going to go square root of that guy squared, right, plus, what's the other one, 20.298. There we go. I'm getting 21.8, I'm going to say 21.90. Okay. Meters per second. Okay, that is the speed. If somebody says, what's the speed that it hits the ground with? Okay, that's the speed. The speed is about 22 meters per second. And now to make it a velocity, we want to find that angle, right? That angle right there is tan minus 1 of the opposite side over the adjacent side, right? So 20.298 over 8.216. So second tan and I expect that angle to be bigger than 45 degrees. Indeed, it's like 67.96. So that's about 68 degrees. Okay, so that's 68 degrees below horizontal with a speed of 22 meters per second. Okay, that would be the velocity in terms of an angle and a magnitude. In terms of vector components, it's 8.216 meters per second in the x direction, plus negative 20.298 meters per second in the y direction, without rounding it to sig figs. Okay, so that's how you do a fairly complex cliff problem. I'm going to solve the other parts, C and D, on separate videos.